Hello, everyone, and welcome to another episode of the Zinc Gland Biology Podcast. I'm Dr. Juliana Amarim, not only your host for today's episode, but also happy to join as one of the moderators for our discussion. Before we get started, I just want to thank everyone for tuning in and remind you that this podcast is part of the initiative to expand our Zinc Gland Biology network. Here we share conversations with researchers from all around the world and highlight exciting work in our field. For this episode, I'm here with Carrie Pernick, our junior moderator, who will help me lead today's conversation. Carrie, would you like to briefly introduce yourself, please?
Yeah, thanks, Juliana. Hi, my name is Carrie Pernick. I'm a research technician in Dr. Isabel Lombart's lab at the University of Michigan with Juliana. And I'm very excited to be here and help you moderate today.
Great, Carrie. I'm now honored to welcome Dr. Gulsan Kazi, Assistant Professor in the Department of Biosystems Engineering at Yamagata University in Japan. Her research spans tissue regeneration, biomimetic materials, and branching morphogenesis in salivary glands. Dr. Kazi holds a BDS and a Ph.D. and has built a rich academic journey from dentistry to advanced regenerative biology. Thank you so much for joining us today, and please use the floor to introduce yourself.
Okay, thank you very much. Julian already told that I'm Dr. Gulsan Ara Kazi. I am from Japan, Yamagata University. And my background is actually I'm a dentist, but now working on the regenerative medicine and in the Department of Biochemical Engineering, Biosystem Engineering.
If that's okay with you, I'd like to start by asking a bit of your background and current work, and then we can move into a more focused discussion on your recent published paper in the Journal of Neurochemistry. Is that okay?
Okay.
Okay, so let's get started, Carrie.
Okay. So Dr. Kazi, you are the first author on the paper of Zinc Modulates Neurturin AKT Signaling to promote parasympathetic innervation in developing submandibular salivary glands. Could you tell us what being the first author meant to you? Was it part of your doctoral or postdoctoral work?
Okay, thank you for question, Kerry. Actually, this is not my doctoral course work. This work I actually start when I joined as a junior assistant researcher in the lab under Professor Takuya Matsumoto, Okayama University. And also, and then I get actually very interest in the salivary gland development. And also for the mint of first author, what I feel like when I get the all responsibility from starting to the conceptualization and then doing the experiment and also, so I think I can explain these things much better than any others. So that is the meant to me as a first author.
Yeah, I think that makes a lot of sense. When we are the first author, we usually say, I know my research better than anyone. So you can ask me any questions and everything is going to be okay. Because I think the first author is the one that goes to the bench and do all the experiments and then has to write the paper. And it's just a lot of work. So you get very involved. But I think who is listening to us, they won't, maybe they didn't read the paper yet. So maybe I'll ask you to tell me what is the main objective of the paper and talk a little bit about your results. And then that way they can follow better what we're talking about.
Okay, so I will just explain in gist. Initially, everybody know that the zinc is very important for the neurogenesis. It's already the central nervous system. The zinc is very, very important. It's already reported. But when we check the parasympathetic innervation, the parasympathetic neuronal growth, actually what happened, how zinc work, what happened in the zinc supplement or something, we don't know. Because as you know, the now people are thinking that zinc maybe work as a therapeutic drug for the Alzheimer or Parkinson disease. Because in Japan, many older people, they are actually taking the zinc just because doctor said, maybe you can use the zinc so you don't have dementia or something. So this actually first thinking when I thought, maybe zinc have some relation also in the salivary gland regeneration maybe occur. So that time this is the first point. So first we try to evaluate the whether zinc have any effect in the salivary gland growth or not. And then because the salivary growth is actually depends on the neuronal innervation. Yes. So, whether zinc have any effect on the salivary gland growth and neuronal innervation. This is the first point I am thinking I was try to evaluate. This was the first objective. Then I found like, okay, so in the disease condition, we have like lot of protective markers for the neuron. Yeah, for example, the neurotrin. So if neuroprotector is not working, whether zinc is work or not, to help to grow the tissue and the salivary gland and the neuron. So next, I try to focus. Okay, what are their connection and how they work. So this is the main objective in my research.
Mm-hmm.
How zinc and the zinc work on the salivary gland development, parasympathetic neuronal growth, and also how it's work on the neuroprotective function, So these three things combined as objective of this research.
So could you talk a little bit about this study, how you design it, and then you perform the eye hydrogel, and then you start to understand how that could modulate the pathway?
Okay, thank you, Juliana. Actually, this work is not a single step work. For example, in my previous work, first I study regarding the neurogenesis, parasympathetic neural innervation. And then, of course, our tissue is like not a single, only the single mechanical QS in our body. So it has like hard area, soft area. I mean, mechanical stiffness is very, very important. So if we try to make some regeneration of the tissue, we have to understand that one. So first I prepared the hydrogel with different types of mechanical stiffness. Very simple way. I just change the concentration and then evaluate that. And then when I evaluate that one, that time first I check like, okay, maybe zinc finger or the zinc, an external zinc maybe have some influence. Because I did first the zinc work and then I check also the neuroprotection.
Mm-hmm.
Then I found like there have some connection. So initial this work actually only this paper work around 3 years it takes for the
Oh,
concept. But if you say like from when I'm starting about the zinc and the, it's actually around 8 years. So
okay.
it's a very long
Wow.
time. Mm.
It's a very long path, right? You start
Yes.
with something and you learn a lot of things and how you can connect different findings, and then it leads to other research, and then you get a paper that is actually based
Yes.
on a long journey.
Yes. So because for young researcher, I will say like when we do some experiment research, first thinking, okay, I am working with someone and then he get this one. Oh, maybe it have like connection with this. So
Hmm.
it's coming like this way. So and then when I found like, okay, zinc have some, so it can go to that more therapeutical way, clinical way. So we start like this, first finding the neuroprotection and then, okay, neuroprotective factor. What is neuroprotective factor have? Then I found some previous work with others researcher like, the Saranox and others. They are talking about the neurotrain and then I make the connection. I found, okay, there is some lot of connection with them. So this is the, in Japanese we said like hikkake.
Okay.
Um, so yeah, so I have a question about bioprinters and how they're, up and coming in the regenerative medicine space. Did you guys use any such technology, bioprinters or anything like that?
Actually, now I don't use, and also like maybe in recent for some few years, I'm not thinking to directly use any bioprinting or something. But actually now I am preparing a new types of hydrogel. I'm trying to synthesize a new type of hydrogel that can be used for the drug delivery on demand. So we can supplement the extracellular zinc. Now I'm focusing on the zinc established as a drug for regeneration of the salivary gland. I'm thinking to go on that way. So maybe that hydrogel, I don't know, maybe we can in future use as for the bioprinting. But in this point, I am not focusing on this.
And when you formulate the gel, you do this with pipetting, or how do you make the gel? Because I had some experience with the bioprinter, and I think it's a very different process than formulating. And
Yeah.
sometimes I feel like formulating can be even harder because you have to be very precise, or your gel is just going to be different from one to another one. And I
Yes.
don't know if that changes for you the outcome that you're looking for. If you make two different hydrogels and something that is just very small is different in between them, and then they just
Yes.
don't work the same. Does that happen?
Yes. Actually, it's happened because now I'm preparing the gel with actually uh, it's common, very common gel like RGD modified hydrogel, because you know the alginate have very lacks of cell adhesion property. Cell is not actually attached. So and as you if you read the complete paper, the zinc paper, you can find that the normal alginate hydrogel I am using as a negative control, the stiffer hydrogel, because when we try to culture the alginate in a stiffer way, gel, the tissue is completely degenerated.
Mm-hmm.
So now but when I add the external zinc or other things, it's changing. The tissue is growing or something. So what I'm doing, like I add the RGD peptide along with the light responsive moiety on it. So we can use the UV light or some other external light exposure. So maybe the drug or can be released on the localized side. So that is my actually focusing now. I'm not focusing. So
Okay.
I modified the light responsive hydro. I'm going to light responsive hydrogel synthesis.
I see.
Oh,
So the idea
interesting.
is to kind of transplant. If you do a transplant there, then you can activate using the light and release the
Yes.
drug that you have.
Yes.
Okay, wow, that's nice. That's very
Yeah, that's really interesting.
Yes.
you are
I
what
think.
kind of light sorry, you can say.
Sorry. No, I
What kind
finished.
of light are you using for that?
Actually, my final goal is like, the head and neck carcinoma. There is like, we use normally after the surgery, we use radiation therapy.
Mm-hmm.
So actually, my target is like that. I mean, after surgery, during the surgery process, if we put that hydrogel on that particular area where we need the tissue regeneration or the, so we put that area, and then when we do the radiation therapy, that radiation will break down the hydrogel, so the
Mm.
drug will release, because the radiation therapy is the main cause of the xerostomia,
Mm-hmm.
one of
Hmm.
the biggest cause. So that release the drug, so that glandular tissue will be continuously growing, and there is no, I mean, even though we put the radiation, maybe the salivary production will be continue,
Yeah.
xerostomia may be prevent. So this is just preliminary thinking. I don't know I can succeed or not, but this is my final goal.
Okay, so if I'm understanding well, the idea is before radiation, you place the gel there, and then with the radiation, that light is going to break the gel down and then release the drug. And
Yes.
we hope it's going to prevent xerostomia to happen.
Yes.
All right, that's actually very interesting. So this paper that you published was the first step for this type of treatment because it's more related to the development, right? So
Yes.
after you see that you can the zinc and the nutrient factor can help the pathway, the PI3K pathway, you plan to do the same, but now with radiation involved.
Yes. Because if we try to prepare, I mean, do the regeneration, we have to know the first developmental stage.
Yes.
So that's why now this is the very initial part, just to understand the zinc, I mean, the like mode of action of the zinc and neurotrin. So now I understand, okay, the PI3 kinase pathway, or like AKT mainly. AKT is working on that. So next step is like, okay, actually now I am working on the more details about the AKT working pathway, because in our paper I found like, as you can see, that PI3 kinase directly have some limitation in the AKT only. So I was thinking that the AKT is working not only through the PI3K, maybe other pathways also involved. So now I am working on that, try to evaluating that one also. That okay, what happened the other pathway, for example, mTOR.
Mm-hmm.
Yes.
Working with pathways is so hard because
Yes.
they have so many connections, and then you don't really know what should I do next.
Yes.
So when you mentioned the biomechanical stress and how this affect to the gland development, could you give us a better example on, I don't know, how can I ask this? Gary, maybe you can help me.
Yeah, when you see like different mechanical stiffnesses within the gel, do you get different outcomes of your drug delivery, or does that answer your question? Or does that
Yeah,
okay.
that's a good question. Yeah.
So actually, uh, this is like this zinc work in the hydrogel. This is maybe my fourth or fifth paper article regarding the mechanical stiffness. So when we first work under Professor Matsumoto, his work is actually he first found that mechanically stiffed hydrogel is actually diminished the tissue growth,
Hmm.
the soft tissue growth, not hard tissue growth, soft tissue growth. So he first found that, and then when we found that one, we try to elaborate more. For example, we use very very soft hydrogel around 4 to 6 kilopascal mechanical stiffness hydrogel, and we found that that is very 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 nicely help to grow the tissue. But when we use around the 100 to 180 kilopascal mechanically stiff hydrogel, the tissue is actually completely deteriorate, no, not growing. And then when we stain it with neuronal staining for tab 3, so tissue actually we found like the neuron is actually not growing.
Mm-hmm.
So we
Hmm.
found that okay, mechanical stiffness actually not only block the different types of interaction between epithelium and mesenchyme, also the neuronal growth is also. So maybe the mechanical force prevent the connection between the cell to cell or something. I mean that one we don't not yet completely evaluate. So I think
Yeah.
so. This is one of the biggest reason, things happened during the mechanical changes in the surroundings.
Yeah,
Okay,
that's really interesting.
you can talk, Carrie.
Yeah, that's a really, really cool discovery about the different stiffnesses and growing neurons.
Yes, I think so. So maybe we need to check this. So this, for example, if we evaluate the clinical side, clinical
Hmm.
consideration. So if there is like surgery, radiation therapy, the stroma, the microenvironment is actually the become more fibrosis like pattern, more high, stiffer. The collagen
Mm.
accumulation has become higher. So what happened in the tissue, surrounding tissue? This is very very important to need to understand for regeneration of that part. So that's why actually we're focusing on the in vitro ex vivo experiment using the different types of scaffold, but not inside, but on the top of that scaffold, we culture the tissue.
Mm-hmm. And for the zinc, putting the zinc now, because that part of fibrosis is very good because it's a clinical translation. And then when you talk about the zinc, is there a critical window during the salivary gland development when the zinc modulation has the most pronounced effect on the parasympathetic innervation? So you know during the development when is the best time to release the zinc and have better parasympathetic innervation?
Uh, Thank you. It's a very, very, very important point we need to evaluate. So initially, now I am checking on during only the just when the salivary gland just start to budding.
Mm-hmm.
So I didn't check actually little bit more earlier stage.
Okay.
So I didn't check it, but I think because the zinc finger is start working when the notochord or the spinal cord is start to growth.
Mm-hmm.
Because so maybe that is the initial stage when the zinc actually start to working. So I didn't check it, but maybe I will take it as a very good point
You have
for
to
my
choose one
future.
time point, right? You could just do all the time points and see what is better.
Yes, so we choose only embryonic in mouse embryonic day 13. I
Yeah.
only check the 13 days, but actually the salivary gland start to grow around 11.5. Embryonic is 11.5. It start to grow start. So maybe if we can check from that point, we can understand more details that actually which time point the zinc start to work.
Yeah. And have you tried to do, since you plan to do this for repair, have you tried to do that not for the development, but after an injury? I know that's one of your plans, so have you tried that already?
Uh, yes, actually, we cultured the tissue inside and the stiffer hydrogel,
Hmm.
and then also like I add the blocker of the PI3 kinase. So tissue is actually start to deteriorate it, and then in the middle of the experiment, we replace that with the zinc,
Hmm.
that blocker, and also like in the stiffer hydrogel where the tissue is already start to diminished or stopped. So we add the zinc, and then we found that that effect is start to recover. We found that.
Yeah.
So this is a very good point for us to think that zinc maybe work as a therapeutics.
Okay. And so, something that I saw on your paper too is there is a difference between the zinc concentration. So if you do a higher concentration, you can actually inhibit the branching. So I don't know if you evaluate something more about the pathway, how this high concentrations are also modulating the pathway, or you just chose your concentration and you were like, I'm gonna do this concentration because I cannot test all the concentration either.
No, actually, it's I mean the when we evaluate the concentration, I think you already see the supplementary data that when we increase the zinc concentration, the tissue is actually completely become distressed. No, not remaining. It's become black, and then I think when we check the cuspous staining, that almost more than 60% cell is dead. So it's not possible for us to use that tissue for pathway analysis, so we didn't conduct that one.
Yeah, yeah, that makes sense. Yeah, I saw in the figures that it doesn't even grow, right? It's just
Yes.
yeah. And you have any clue why, right? Why? So if
Uh,
you
be-
have a higher concentration of zinc, that's not good.
because actually zinc is already reported like zinc have the I mean the zinc toxicity is very biggest issue. If you have the higher amount of zinc consumption, it causes the toxicity in the body and the cells. It is already reported in a lot of. So maybe that is the one point that we need the zinc in a trace amount. This is trace element. So we cannot increase beyond this.
Yeah,
So this is one of the biggest challenge if you actually use this one as a drug.
yeah. Yeah, I think that's something important for all the drugs, right? It's always
Yes.
not always, but a lot of the times dose dependent. And then if you just
Hmm.
put too much, it's not
Yes.
good. So we have to know the what is the best.
Optimum level. Yes.
Yeah, the optimal. Yeah. Any questions, Carrie?
Yeah, with the findings of the appropriate zinc concentration to use, do you think that a zinc supplement is a potential strategy clinically to be able to repair the nerve damage after radiation? And how would we be able to move it forward in a clinical application?
Actually, till now, I'm using a particular concentration of the zinc, and as I told that the radiation therapy, I'm trying to use that radiation therapy for breakdown of the gel and the release that zinc. So now, actually, I'm doing that one. that experiment that actually after transplant the gel, we including the zinc inside the in vivo condition, and how much zinc is actually now releasing after breakdown the gel. So that is actually now I'm doing. I did once, and I found like it is also dose dependent. It was like with the day the release is actually like cumulative release happened, but this is only the release inside outside the after breaking the gel, and then I just analyze the liquid, so not yet implant inside the body. So maybe I have to check that one using the different concentration of the zinc, because I don't know how much zinc will be released. So
Yeah.
not yet. We do not know yet that
And
one.
how do you analyze the zinc release in the tissue? How can you make this evaluation?
Now I am doing the water is ICP-MS analysis, but maybe I don't know, but I am thinking that first I will evaluate the surrounding tissue with the uh, Western blot or something, but only the zinc presence of zinc or not, and maybe we have to extract the tissue fluid and
Mm.
then analysis that using the ICP or something. But I have to consider different types of procedure. We
Yeah.
don't we do not know yet. I mean, exact what is the optimum method
Yeah.
can
Yeah.
give us that result.
Okay. So that's also a challenge.
Yeah, so
Yes.
I was gonna say it sounds like that'll definitely be a challenge to see the concentration that's actually being released.
Yes, I think so. This is a very big challenge for me now.
But I think it's going to be a very important finding too when you decide what is the concentration. Because as you said, you can have a concentration in your gel that's going to be good in vitro, but then you don't know how much you're going to be releasing of that concentration. So if you
Mm,
get the point that you know how much you're releasing and how what is the concentration you need, then you can do very good progress with that.
yes. So I'm now doing that one, the in vitro releasing the after radiation, in vitro releasing how much I'm doing that or in vitro. So if that amount is actually constant, so maybe when we put in the inside the body, so and then I put the radiation therapy. So maybe I am expecting, this is my hypothesis, maybe the almost similar amount will be released. So and then I can check the whether this is toxic or not. Maybe that time I can confirm. Okay, this amount is actually optimum for the in vivo condition or something.
Yeah. Okay. And how does the zinc specifically influence the neutron AKT signaling pathway? Is there a direct connection, like it activates directly, or is indirect effect?
I think this is when I mean, okay, I will just example my experiment, the paper that I write. So when we add the neurotrain, actually, after blocking the anti-neurotrain, I block the tissue, I mean, the neurotrain work, and then I put the zinc. I found like actually that blocking is not effective anymore. So I was thinking, even there is any blocker for the neurotrain, neuroprotective function blocker, zinc can overcome that one.
Mhm.
So maybe it is like combined effect in a
Yeah.
particular time point. So it's not like I mean after blocking or after stopping the work. Maybe it's combined.
Yeah.
So this is my I mean my thinking.
So, do you want to give any final reflections to our listenings about your work and how important that could be to the clinical view in the future? I know this is a very long path. So now you're doing in vitro studies, and to go to do the transition from now to the clinic, that takes a long time. But if you have any comments that you want to do and make for the young people too, to maybe join your lab and help you out so you don't have to do all the work alone, and also to engage in this type of research, because the basic research leads the research in the clinic anyways. So if you have any messages that you want to give, we would love to listen to it.
Okay, thank you, Juliana, for give me such an opportunity to talk with the young researcher. So actually, this is a very important point of the new salivary. I mean, I'm working on the salivary gland branching morphogenesis, but not only the salivary gland branching morphogenesis, many of other glandular tissue also have the similar tendency of the tissue growth. Maybe, for example, the kidney. Kidneys neurogenesis is little bit later than the salivary gland. Kidneys first come to the artery development and then come the. So I am also checking that one. So maybe if we can actually confirm that okay, zinc can be used as a therapeutics in the, but I think it will take at least 10 to 10 years because it's a very 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 long process, and if I really want to use as a drug, it's really very long way to go
Hmm.
because for the toxicity of the zinc.
Yeah.
It's a very, very biggest point. We have to pinpoint amount, choose the pinpoint amount of the zinc, and then the particular in which time point we need to really use this drug. So this is a very so first we have to understand the zinc work, zinc work, how zinc uh, connect with the all types of tissue, because glandular tissue is not only the epithelium, not only the mesenchyme, not only the, it has all types of tissue together. And also like salivary gland have like cell, different types of cells like acinar cell, myoblast, and so this is a very complex tissue. And the zinc, where in particular which area is zinc working, now we are found like it's near to the basement of the epithelium junction. So we have to check that one also more clearly, clarify, we have to clarify that point. So whether it is in the myoblast or only the basal cell. So this is also very nice point. So maybe if a researcher actually want to work this work, they can choose this part also, or they can ask me any question that I can help them. So final the hydrogel that I mentioned, if we can succeed, this is also related with the not biologist. This can be related to the chemist, chemical researcher. Yes. So I think the young researcher can take the point from that area. They can contact with me or they can doing there by themselves. So it's I hope they will get a lot of knowledge also from today's podcast interview
Yeah.
regarding this point. Okay, thank you very much for giving me this honor.
I really like that you mentioned other organs because I think we're biased and we we keep talking about salivary glands, but we do want people to join us talking about other organs too. So I think
Yeah.
that's a good opportunity to invite people to come here and talk about other organs than the salivary glands. And I'm happy that you were doing this research too. So you're trying to bring together different organs for your own research. I think that's very, very interesting.
Thank you.
So thank you so much for joining us for this podcast and to share your expertise with us. I also hope people can get a lot of takeaways from this talk because it was very good for me. I learned a lot with you. And I think we provide a very interesting discussion. So I thank you very, very much to be here with us today and for your time. Thank you, Carrie, too, for being with us and to join me in this discussion and this challenge of asking questions about
Yeah.
work.
Of course, Juliana. And thank you so much, Dr. Kazi, for talking about your work. I'm really excited to see more about your work with the radiation and breaking up the hydrogel. So I'm looking forward to seeing your future papers.
Thank you very much. Hopefully, we can I can give you all some new information regarding this in near future. And also, actually I would like to thank Juliana and Kerry for giving me such opportunity to talk about regarding my research, and then it can also help to others researcher who is actually now trying to enter in this field. So thank you very much.
We will have you here in some years ahead and talking about what is the best dose of zinc, how can we release all the concentration we need, and also
Yes,
about other organs.
yes, thank you.
Thank you so much. To our listeners, thank you for being with us. We hope you enjoyed today's podcast. If you haven't already, make sure to subscribe to the Exocrine Gland Biology podcast channel so you don't miss the next conversation.
And please contact us if you're interested in being on an episode. We would love to have you and interview you and ask you questions all about your work.
You can also share this episode with your colleagues and peers who might find it interesting. That is a great way to help our community to grow. Our next episode will be coming soon, so stay connected. And until then, thank you for listening, and I see you next time.